Hello everyone, welcome back. This is the second video in the series of the videos of geometry using complex numbers. In this video, I'll discuss in detail mostly the theoretical part of the the geometry using complex numbers, and I'll focus the most on the concept clarity rather than using the integrity of how to solve the questions. So let's see. In this video, the first topic that I have taken is subtraction of complex numbers. Suppose that there are two complex numbers, Z1 and Z2, right? And we have to find the difference of the complex numbers Z1 and Z2. So let's first write it. Suppose Z1 is equal to x1 plus iota y1 and Z2 is equal to x2 plus iota y2 are two non-zero complex numbers. First of all, you must watch this video till end because the video length is 37 minutes and this video covers broadly many different topics that is used in solving the questions of J Advanced, J Main and other engineering examination. In fact, ISI, CMI and other exams also. So generalized Z2 is equal to, simply subtract real part with real part, imaginary with imaginary part. So we are getting x1 minus x2 plus taking iota common y1 minus y2. So if I take the modulus of the complex numbers Z1 minus Z2, this is equal to square root of x1 minus x2 whole square plus y1 minus y2 whole square. Very simple. Now these are all the mathematical thing. Now how to interpret it geometrically? So you already know that in coordinate geometry this is called the distance formula. So it is actually the distance between the points with f(x) x1 plus iota y1 and x2 plus iota y2 in complex plane, or in coordinate plane it is distance between the points whose coordinates are x1 y1 and x2 y2. Now let's see how can we interpret it in more detail in complex plane. Let's say this is real axis, and or say same as x-axis in Cartesian plane, and this is imaginary axis same as y-axis in Cartesian plane. This is origin. Now suppose that there are 2 points in the complex plane, and these 2 points represent the points with f(x) as z1. Other point, let's say that this point is p2 with f(x) as fx z2. And if I use the vector concept, then let us say that the this op1 vector represents complex number z1 and op2 vector represents complex number z2, right? Now if you see z1 minus z2, which means op1 vector minus op2 vector, this is nothing but p2 p1 vector. Very simple. In vector concept it is p2 p1 vector. z1 minus z2 represents p2 p1 vector. So therefore mod of z1 minus z2 represents the length of p2 p1 vector, and you can say in short distance between p1 and p2 with f(x) is z1 and z2. So z1 minus z2 represents op1 vector minus op2 vector, and this is equal to p2 p1 vector, right? As I said. Now if I ask you to elaborate it in further detail, that in the last video we had seen that the resultant of the vectors z1 and z2 is z1 plus z2, and that is obtained by drawing the parallelogram, right? So if in this video also, in this case also, if I draw a parallelogram, let's say, and let's see that in later, let's see that later. So in this case let me write so mod of z1 minus z2 is equal to mod of p2 p1 vector, and this is equal to under root x2 minus x1 whole square plus y2 minus y1 whole square. Simple, very simple. Now as I said, it is the distance between the points p1 with fx z1 and p2 with fx z2, similar to the points in Cartesian plane with p1 as coordinate x1 y1 and p2 as coordinates x2 y2. In place of coordinates we use fx's in complex plane, so with fx's z1 and z2, right? Now if you have understood up to here, then let's move on and complete the parallelogram. Now we are about to relate z1 plus z2 vector and z1 minus z2 vector. So z1 plus z2 vector is the diameter, you can see this diameter op3, and z1 minus z2 is the another diameter, that is p2 p1 vector. So the difference vector or the addition vector are actually the two diagonals of the parallelogram, right? So OP3 vector is Z1 plus Z2 and P2 P1 vector is Z1 minus Z2. So this is very simple, very easy to remember. Now based on this, let's solve a question, and this question is based on this concept only, and we will try to use as much geometrical approach as possible. In fact, up to 90% we will use only geometrical approach, and the benefit of using geometrical approach is that you can simply visualize the diagrams in your mind, and from there also you can find the answer without using pen and paper also. So in no time you can give the answer. Like if you are using pen and paper, then in that case calculation takes time, but if you simply visualize the concepts in your mind, simply draw the diagram in your mind, then you can solve the question very fastly. Now see, the question is saying that suppose Z1 and Z2 are two non-zero complex numbers such that modulus of Z1 minus Z2 is equal to modulus of Z1 plus Z2. What does it mean? You already know this. Then find the value of modulus of argument of Z1 minus argument of Z2. Now this question, argument of Z1 minus argument of Z2, requires that you have to imagine two complex numbers, one with Z1 and Z2, one with argument theta 1, other with argument theta 2. We'll see the solution very short later, but I'll encourage you to pause this video right here and you should try this question yourself. If possible, try to solve this question without pen and paper, but if you are studying the concept for the first time, then you might feel tempted to use the pen and paper, so no problem. Let's see the solution. Solution is that, let's say this is horizontal axis, vertical axis, and of course horizontal axis as we know is real axis, and vertical axis as we know is imaginary axis. Now let us assume 2 points with affixes Z1, other with affixes Z2, and let us complete the parallelogram. As we know in case vector, we complete the parallelogram. So this is point A with affix Z1, other is point B with affix Z2, and this is C vertex. Let's say this vertex is C, so this is basically the resultant of Z1 Z2, so Z1 plus Z2. Now this diagonal represents Z1 plus Z2, so length of this diagonal represents mod of Z2 plus Z2. Other represents Z1 plus Z2, so mod of other diagonal is length of other diagonal is mod of Z1 plus Z2. So therefore, since it is given that mod of Z1 plus Z2 is equal to mod of Z1 plus Z2, which means that mod of OC vector is equal to mod of BA vector. Very simple. Now since mod of OC vector is equal to mod of BA vector, so therefore length of diagonals of the parallelogram are equal in length. Now the parallelograms whose diagonal are of equal in length can be either rectangle or a square. In both cases, the angle between their sides is equal to 90 degree, right? So angle between the sides, adjacent sides of rectangle is also 90 degree, angle between adjacent sides of a square is also 90 degree. So in this case, we have to find the argument of Z1 minus argument of Z2, modulus of argument of Z1 minus argument of Z2. So let's say that OACB is a rectangle, let us assume, because it can be a square also, we don't know. So let's say this is a rectangle. So angle between the adjacent sides must be equal to 90 degrees. So angle between OA vector and OB vector must be equal to 90. Let's say this angle is theta 1 and this angle is theta 2. So from here we are getting theta 1 minus theta 2 must be equal to pi by 2, 90 degrees, right? So mod of theta 1 minus theta 2 equal to 90 degrees. Now what is theta 1? Theta 1 is the argument of complex number Z1. As you can see, very simple. Theta 2 is the argument of complex number Z2. So replacing theta 1 and theta 2 by our argument of Z1 and argument of Z2, we are now finally getting the answer that modulus of argument of Z1 minus argument of Z2 is equal to pi by 2. Very simple to solve, and once you have solved this question right here, you can close your mind, you can close your eyes, and then you will visualize this solution in your mind. You can easily solve this question without pen and paper also. Once you have practiced, then simple questions can also be solved without pen and paper, just by visualizing the diagram, correct diagram in your mind, and then doing a bit of calculation in your mind also. Then this question is easy, in fact very easy. Now let's move on and see the next concept, or before the next concept, maybe possible that we can see another question. Now this question is very simple. This question says that is this possible that see, the question is being written on your screen. Is it true that argument of z1 minus z2 is equal to argument of z1 minus argument of z2? Is this possible? It is talking about possibility. Or is it true for any at least one pair of z1 z2? Is it true? Where z1 into z2 not equal to 0, which means both are non-zero complex numbers. So z1 is not 0, z2 is not 0. So length of corresponding vectors is non-zero. Now I'll encourage again you to pause this video right here and you should try yourself this solution of this question. But if you want to see the solution, let's see. This is real axis and this is imaginary axis, and just assume 2 points in the complex plane with fx's z1 and z2. So let's say that this point and this vector and the other vector, this represents the complex numbers z1 and z2. So this will represent z1 minus z2. This as we have seen very short earlier, that this represents z1 minus z2. If you complete this and if you extend this vector backward, and let's say that this angle is theta 1, this angle is theta 2, and angle between the vectors is theta, let us assume. And let us say that this subtraction vector, difference vector, it makes an angle theta dash with the real axis. So argument of z1 minus z2, let's say that this point is A with fx z1, this point is B with fx z2. So argument of z1 minus z2 is nothing but the angle that a BA vector is making with real axis, that this is theta dash. So argument of z1 minus z2 is nothing but it is theta dash. Very simple, because z1 minus z2 is the vector BA, and BA vector is making angle theta dash with positive direction of real axis, and therefore argument of z1 minus z2 is equal to theta dash. Now argument of z1 minus argument of z2 is theta. Let me first complete writing this. So argument of z1 minus z2 is equal to argument of BA vector, and when BA vector is extended backward, it's making an angle theta dash, this series. Now argument of z1 is theta 1 and argument of z2 is theta 2. So argument of z1 minus argument of z2 is equal to theta 1 minus theta 2, right? And this is equal to theta. So they are asking that is it true that theta is equal to theta dash? Now it can be true, it cannot. It may be true, it may not be true. Theta can be equal to theta dash in some cases. In some other cases it may not be equal. So theta may not be equal to theta dash. So correct answer should be maybe. Answer is maybe. Maybe it is possible that theta equal to theta dash in some cases. So let's write the answer. Answer is maybe. Answer is asking is it true? Answer is maybe. Next. So till now I've shown you what is the meaning of z1 as z2 and how to represent z1 as z2 in complex plane. Now let us move on and let's see another concept. Let's say this is real axis, this is imaginary axis, and let us assume that there are 2 points in the complex plane. Let's say that these 2 points are in the complex plane and join them. Now suppose that I'm extending this vector. Let's say the first point is A with fx z1, second point is B with fx z2, and I have extended AB vector in forward direction that meets real axis at some point. Now if I ask you what is mod of z1 minus z2, so you already know it is equal to length AB. Now other thing is that so in other words we can say that mod of z1 minus z2 is also equal to distance between the points in complex plane whose fx's are with fx's are z1 and z2. So distance between points with fx's z1 and z2, that is the same as AB in this case. Now the main question is that in this case, let's say the angle, this is theta. So if I ask you the argument of z1 minus z2, so argument of z1 minus z2 is equal to argument of the BA vector, and BA vector makes an angle theta with real positive direction of real axis. So argument of z1 minus z2 should be equal to theta. Very simple. Now in second case, what is the argument of z2 minus z1? So in that case, the direction of the vector will change, and As you can see here, the vector in this case z2 minus z1 vector will be AB vector, so in opposite direction as it was shown previously. In this case it will be opposite direction. So this is AB vector, and if I extend AB vector in forward direction again with dotted line, then the angle that AB vector is making with the positive real axis is what? Can you tell me? Yes, it is pi minus theta, because other angle is theta, so complementary angle. Since these two are complementary angles, so other angles will be pi minus theta. So argument of z2 minus z1 should be equal to this pi minus theta. But this I'm telling you is obviously it is the magnitude, because in opposite direction, since you are taking the angle in opposite direction, so it should be negative of pi minus theta. But magnitude wise, you can say it is equal to pi minus theta. Okay, so magnitude wise, argument of z2 minus z1 is equal to pi minus theta. It is not that this actually whatever I have written here is not correct. Conceptually it should be minus of pi minus theta, because magnitude of angle is pi minus theta and it is in clockwise direction, and therefore the argument of z2 minus z1 should be equal to negative of pi minus theta, that is theta minus pi. Okay, now if you add the magnitudes, then you are getting theta plus pi minus theta, that is equal to pi, that is okay. But if you see the direction also, then argument of z2 minus z1 shall be equal to negative minus of pi minus theta. Now let us see the next concept, that is multiplication of complex numbers, right? Now in case of multiplication, I'm considering the multiplication of two complex numbers z1 and z2. So suppose that let z1 is equal to, I'm writing in this case the complex numbers in Euler form. So let's say that z1 is equal to r1 into a to the power iota theta 1 and z2 is equal to r2 into a to the power iota theta 2, where r1 is modulus of z1, r2 is modulus of z2, theta 1 is argument of z1 and theta 2 is argument of z2, and where z1 z2 both are non-zero complex number, which means r1 not equal to 0 and r2 also not equal to 0. Both have some non-zero magnitude, non-zero modulus. I'm considering that you have already studied the Euler form of the complex number, and only then you are studying the geometry portion of the complex number. So this is real axis and this is imaginary axis. Let us draw them. So the first is z1. Z1 has, you can also represent z1 by r1 vector with angle theta 1. This is r1 vector with angle theta 1. Very simple. And you can represent z2 with r2 vector also if you wish. Otherwise you can simply write the magnitude. So let's say this is the point B with fx z2, or its OB, length of OB, O is the origin, is r2, and this angle let's say is theta 2 and this angle is theta 1, because this angle theta 1 theta 2 are their arguments. Now if I multiply this z1 and z2, mathematically it is very simple to multiply, because z1 into z2 should be equal to r1 into r2, and e to the power theta 1 into e to the power theta 2 can be written as e to the power, okay, there is a simple, very silly mistake written, typing mistake here. It should be r1 into e to the power iota theta 1, other should be r2 into e to the power iota theta 2, so iota is missing here. So okay, you already know, since you are versed in this Euler form, so consider this written as iota theta 1 and iota theta 2 instead of theta 1 theta 2 simply. So if I multiply z1 and z2 together, so what you are getting is z1 into z2 is equal to r1 into r2 and then equal to r, now iota, I'm correcting it now, so iota into theta 1 plus theta 2. Okay, now suppose that z1 z2 is a new complex number, and in Euler form z1 z2 is equal to r into e to the power iota theta. I'm assuming this, that since multiplying two complex number gives a new complex number, so let's say that z1 z2 is a new complex number, and in Euler form it is equal to r into e to the power iota theta, where r is modulus of z1 z2 and theta is argument of z1 z2. Now since it is equal to r1 r2 into e to the power iota theta 1 plus theta 2, so from here we are getting is that r is modulus of z1 z2, so therefore from here we are getting modulus of z1 z2 is equal to r1 r2. Now what is r1? R1 is modulus of z1, r2 is modulus of z2, so mod of z1 into mod of z2, very simple. Now if I ask the argument of z1 z2, so it is theta, so argument of z1 z2 is equal to theta. And what is theta equal to? Theta is equal to theta 1 plus theta 2. Theta 1 is argument of z1, theta 2 is argument of z2, so argument of z1 plus argument of z2. Very simple. This way we can easily find You can easily prove also the modulus of property of modulus of complex numbers. Similarly, property of argument of complex number. You already know them. You already know them, and that's why only you are studying this geometry of complex numbers. Now, the fact is that the argument of the complex number z1 z2 is theta 1 plus theta 2. So if we go further theta 2 in the same direction from the position theta 1, so the net angle we are getting is theta actually. So theta is nothing but theta 1 plus theta 2. So the entire angle theta 1 plus theta 2 can be represented by theta only. Okay, so this angle is theta, basically theta 1 plus theta 2. Now you can say that this is r vector, and you can say fx wise this is the fix of this point is z1 z2, and the length of the new complex number z1 z2, or you can say distance of the point whose fx is z1 z2 from origin is r. Very simple from here, and our since argument is theta 1 plus theta 2, so I have just rotated OA vector by theta 2 to get the new position in theta 1 plus theta 2. And if you r is equal to r1 into r2, very simple, as we have seen just short earlier, r is equal to r1 into r2, that is this r, yes, length of this new vector corresponding to z1 z2. So shortly, in short, we can explain that this r vector has been obtained by rotating OA vector by angle theta 2 and then scaling its length so that its length becomes equal to r1 into r2. So you can say that you're just multiplying, or you're just reducing the r1 length by a factor of r2. So net is r1 into r2. Now if we move further and see the next concept, then we can see that a rotation, as I was talking about the rotating OA vector by an angle theta 2. So let's see the rotation concept from very basic, right? So let us say that we have a complex number z, and it is in Euler form, it is equal to r into e to the power iota theta, and iota in Euler form can be written as e to the power iota pi by 2. So if I multiply these two complex numbers together, which means iota and z, if I multiply iota and z, so I am getting iota into z is equal to r into e to the power iota, taking iota common, theta plus pi by 2. So which means that the new complex number, that is iota into z, has the same magnitude or same modulus as the complex number z, but the argument of the new complex number iota z is increased by an angle pi by 2. Which means that if I assume, let's say that this is real axis and let's say this is imaginary axis. So if we assume in this complex plane a point, or you can say a vector, r vector, and suppose that this vector is corresponding to a point a whose fx is z1. So the new complex number iota z will be 90 degrees shift from its old position, that is OA vector. So let's say that the new vector is obtained by rotating the OA vector by an angle positive 90 degree in anti-clockwise direction. So the new length of the new vector is r, and let's say that this is point B. Suppose that this is point B, not A. A is already there in the first quadrant. Suppose that this is point B, and fx of point B is surely iota z, because fx of point A is z. So rotating the OA vector by 90 degree, the new complex number we are obtaining is iota z. So fx of point B is iota z, and the length of both OA and OB is r. So it is just like that you are rotating this OA. Its angle, initial angle is theta, and rotating further by 90 degrees, so the final angle we are getting is theta plus 90 degree, theta plus pi by 2. And so iota z can be obtained by rotating z by an angle positive 90 degree in clockwise direction about the origin. It is very important about which point, so about origin. Okay, so in that case we will obtain the position of new complex number iota z in the complex plane simply by multiplying any complex number by iota. Its corresponding vector gets rotated by 90 degree in anti-clockwise direction. This is the concept. And since OA is equal to OB, as you can see here, OA is also equal to R, OB is also equal to R, so therefore OA is equal to OB. Length of the vector z is equal to length of the vector iota z, and we also know that mod z equal to mod of iota z. So from there also we can conclude this. Now let us draw this rotation for clarity, for further clarity. And OB vector is obtained by, as I said, by rotating OA vector, and mathematically it is obtained by multiplying the corresponding fx by iota. In this case the fx of OA vector is z, so multiplying z by iota we are getting iota z as the fx of new vector, that is OB vector, right? So in whatever I've written is in terms of vector, let's write it is in terms of complex number. So if z is a complex number which is multiplied by iota, then new complex number, that is iota z, or you can say is obtained by rotating the vector z by an angle 90 degree, or you can say then the vector z gets rotated about origin in a complex plane by positive 90 degree in anti-clockwise direction, right? So this is the rotation concept. Very easy, very simple. Now let's move on and let us see another concept. These are similar concepts actually. These are very similar concepts actually, but these are very basic and fundamental concept. If this is strong, it is very easy for you. Let us say there are 4 points in the plane, and these 4 points are equally distant from origin. Let's say the point A has a fixed z. If I rotate the vector OA by 90 degree in anti-clockwise direction, we get the new vector whose fx is iota z. And if I rotate OA vector in clockwise direction by an angle 90 degree clockwise, what we shall get is minus iota z, or you can say that is same as z bar, point B as in this diagram. So point B, so OB vector is obtained by rotating OA vector by an angle 90 degree in clockwise direction. So therefore z bar can be written as minus iota z, and this point, new point minus z, is nothing but it is the image of z with respect to origin. So as I said, z bar is equal to minus iota z, because either you write this is conjugate of z, or you can write that this is obtained by multiplying z vector with minus iota. So from 90 degree anti-clockwise rotation we are obtaining iota z, and from 90 degree clockwise direction we are obtaining minus iota z, which is same as z bar, right? And very simple. You can also verify, assuming z is equal to x plus iota y, we can say that z bar is equal to minus iota into x plus iota y. Very simple. So minus iota into z. Okay, this further rotated by 90 degree gives you minus z, because iota square into z is minus z, and this is further rotated by minus 90 degree, you are again getting this. So iota into z bar, sorry, minus iota into z bar must be equal to minus z. Minus iota into z bar must be equal to minus z. Very simple. From here all of them are equally distant from the origin, so therefore mod z equal to mod z bar equal to mod iota z equal to mod of minus iota, and these all modulus are same because all of them are equidistant from the origin. Okay, let's move on and see a question, and this question is fabulous, one of my favorite question that uses pure geometry in complex plane. And see how smartly this question have been solved, and how we can solve this question using minimum calculation and maximum drawing. If you can draw and simply visualize, then you can easily get the answer with least calculation. You don't need to do the calculation further. With least calculation you can obtain the answer. So question is saying that find the area of a triangle in complex plane whose fx's are z, iota z and z minus iota z, where mod z is equal to 6. You can see that z minus iota z is nothing but it is resultant of the vector z and minus iota z. So first of all, let us draw real axis and imaginary axis, and let us say that there is a point in the complex plane whose fx is z. Let's assume this point in first quadrant. So let's say that there is a vector corresponding to that point, and let me draw it. So let's say that this vector is a vector corresponding to point A with fx z. Now if I multiply z by iota, we are 90 degree apart from OA vector. Let's say that the new position is point B with fx iota z. Very clear? If I multiply z by iota, we are getting iota z, and that is 90 degree away, 90 degrees shift in anti-clockwise direction. Similarly, if I take the image of iota z, or you can simply say that if I multiply z by minus iota, then this vector will get rotated in clockwise direction by an angle 90 degree. Now if I join z and iota z, so this line, this dotted line will be the resultant. This, see this I'm drawing. So this will be the resultant of z and iota z. So this vector will represent z plus iota z. And as I said, if I multiply OA vector by iota, which means if I minus iota, which means if I multiply z by minus iota, the new position we obtain has the fx minus iota z. Or other way to explain is this, that you just take the image of point B with respect to origin. So fx of B is iota z, so fx of C is minus iota z. Very simple. Now if I join them, and this will be the new vector, whatever we are getting, this will be nothing but minus iota z minus z. If I complete the parallelogram in this case, then the new position, this position is in fact the resultant of the vectors z and minus iota z, which means z minus iota z. So affix of the new point as after completing the parallelogram is z minus iota z, because this is the resultant of the vectors z and vectors minus iota z. So the new position, that is the new vector, I am drawing it with dotted line. Wait. So new vectors shall have the corresponding affix as z minus iota z. So let's first draw it. So drawing now, see here. Okay, so as we have seen that the vector AB, you can see in the diagram, the vector AB is also z minus iota z. Vector AB is also z minus iota z. So if I join origin with the new position D, it is again z minus iota z, because these two are parallel vectors. So therefore OBAD, see, OBAD is now a parallelogram, because dotted line is parallel with dotted line, solid line is parallel with solid line. Which means OB is parallel to DA and BA is parallel to OD. So this is a parallelogram, and your required triangle, the triangle that question is saying, is nothing but triangle BAD. I have marked it with blue dots. The vertices of the triangle are marked with blue dots. So see this. So BAD is the triangle whose affixes are z iota z and z minus iota z. So this, as I said, is the triangle with vertices z iota z and z minus iota z. Now since it is half of the, since the area of this triangle is nothing but the half of the area of the parallelogram, so by any method, if you can find the half of the area of the parallelogram, then you are done. Now as you can see that OA is also the diameter of the same parallelogram, and therefore OA also divides the area of the parallelogram into equal parts. So basically the area of triangle BAD is same as area of triangle OAB. As you can see, area of triangle BAD is same as area of triangle OAB, because both of them represents half of the area of the parallelogram. So area of triangle BAD is same as area of triangle OAB. But area of triangle OAB can be found very easily, because it is the right angle triangle, and area of right angle triangle is half into base into height. Very simple. So required triangle is triangle ABD, and area of triangle ABD is half of the area of the parallelogram OBAD. I'm writing it very slowly. Wait. So area of triangle ABD is half of area of the parallelogram OB. Oh wait, area of the parallelogram actually. So area of the parallelogram OBAD, as you can see. Now half of the area of the parallelogram OBAD is same as the area of triangle OAB. So we can write this is equal to half, this is equal to area of triangle OAB. Very simple. You can visualize it in the diagram. You can see the diagram. So half of area of parallelogram OBAD is equal to area of the triangle OAB also, right? In geometry, if you remember that if the two triangles are formed on the same base and between the two parallel lines, then their area must be equal. In this case also, area of triangle O A area of triangle BAD and OBA are same, or OAB you can say are same, and OAB is a right angle triangle. You can say AOB is a right angle triangle, so its area must be equal to half into base into height. Half into base, let us say that base is OA and height is OB. So OA is equal to mod Z, as you can see from the diagram in your note. OA is equal to mod Z and OB is equal to mod of iota Z. Now mod Z and mod of iota Z both are same. So we can write that this is equal to half of mod Z into mod of iota Z. This is equal to half of mod Z into mod Z, because mod iota Z is nothing but mod Z. So mod Z into mod Z, that is equal to mod Z square by 2, or you can say half of mod Z square, that is equal to, since mod Z is given as 6, so mod Z square is 36, so 36 divided by 2, which is equal to 18 square unit. Now this is done, this question is solved. Only this much calculation, but that is also done to show you, otherwise there is no need of doing the calculation here. Okay everyone, what I feel is that you must have understood the concepts in detail and deeply, and you have to retain the concepts till your exam at least. And I have tried to deliver as much as possible in terms of geometry or purely geometry. Whenever it was much required to write the narration, write the explanation, and to do the calculation, I have used them as less as possible. Okay, so I hope that you have enjoyed the video, and stay tuned for the next videos. And surely if you, with this video, if you revise with the previous video and then you come to watch this video, that will be much beneficial for you, I think. So everyone, I'll meet you in the next video. Be ready, be prepared with the last two videos. Next video is going to be awesome, even much better than these previous two videos, because these two videos are for beginners only, those who are not acquainted with at least the geometry of the complex numbers. See you then. Bye bye. Bye everyone. Take care.